So hello, today I'll be presenting my experimental project for Physics 101 at Bilkent University, and it is of a simple pendulum with differing initial angles. So when it comes to our background information, a simple pendulum is a mechanical device that oscillates in motion, and it is made up of a mass and a string of length L, and it demonstrates periodic motion in a really simple way. And my methodology includes, just a pendulum released for different initial angles. And I'm going to be using a camera to record the total time of 10 oscillations of each angle. And then I will be calculating the time period of each angle by dividing this by 10. And theoretically, I will also be calculating the time periods using this small angle approximation and these two approximations for smaller and larger angles. My setup is sort of like this. So I have this is a table and I use a ruler in there. This is the pendulum stand. This is my strength of 0.75 meters. This is my mass block of 0.192 kilograms. I have my stable camera, and this is the paper marked with some initial angles. So my procedure goes like this in this video. I get the rope to align with a selected initial angle from the paper. Then I just let the bob go. And then I just record this and for like 12 oscillations. And then I'm going to be using iMovie to determine the total time for 10 oscillations. So this is my data. Using iMovie, I get this. For the 25 degree angles, it became too unstable, so I just decided not to proceed with those. This is my process data. So this is the mean time for 3 trials, and this is the average empirical time period divided by 10. This divided by 10, so that it's just the time period. And here is my calculations. For the small angles, so 5 and 10 degrees, I'm going to be using the small angle approximation, which is this value of the time period for every angle. And for the larger angles, so 15 and 20 degrees, I'm going to be using both Bernoulli's equation of this and Parwani's equation of this. So for error calculations, I used for 5 and 10 degrees, so that is the smaller angles, the small angle approximation results. And for 15 and 20, these two larger angle results. And my uncertainty is 1/30 because it's a 30 FPS camera. So here are my results tabulated. Here I have my measured empirical time period of each angle. This is the small angle approximation results. This is Parwani's and this is Bernoulli's equations results. So we can see that these two actually yield the same results, but my empirical time period actually deviates a lot from the theoretical parts. And the small angle approximation does not really correlate with either the empirical or the theoretical parts for like the largest angle. So we can say that the small angle approximation is not accurate for larger angles than, like, say 10 or even 5 degree pendulums. So here we come to the discussion part. I related this deviation of the empirical time periods with the theoretical time periods to damping. So damping occurs in harmonic oscillators when air friction is there. So that is, in every practical experiment. And it causes a decrease in maximum wave amplitude and an increase in the time period. And we can see this a lot more and a lot clearly with the larger angles, which is, in my video, it's quite visible. So we started from this, now it's up there, right there. That is damping. So therefore, for my evaluation part of the experiment, we can say that it is important to investigate the feasibility of varying length of the string and mass of the block to theoretical models to avoid systemic differences. And maybe that's why my empirical results and my theoretical results actually were quite different. And I should have used many more measurements with I could have gotten more clear data, but I did not want to experiment with higher angles because, of instability. But I could have used smaller increments, such as like instead of 5-degree increments, I could have used 2-degree increments to have more measured data. And actually, a high error comes from the additional geometrical variables. That is, that practical simple pendulums are not linear, they are more conical. So I could have used, a conical pendulum-based models for my theory. And instead of a cubical block, I could have used a spherical bob to decrease air friction. And I could have used a higher frame rate for my camera to decrease my uncertainty. And again, a better video processing done, frame by frame, maybe computational, to get a higher accuracy. So these are my references, and that's the end of my presentation of my project.